Hi, and welcome to this new video about kernel memory, in which I expand the previous video and trying to explain how why this is difficult to choose the right embedding generator, and why sometimes people simply try to use a custom embedding generator and they fail and the RAG solution does not perform very well. And this is of paramount importance that when you choose an embedding generator for your scenario, you carefully read the documentation. In the previous example, I show you where I use the all-MPNet embedding generator by SBERT. It's if you look at the statistic, it seems really, really good, but you need to read the documentation carefully. If you go on the SBERT site, and SBERT, I remember you is sentence BERT. It's sentence bidirectional encoding representation transform. It's a particular version of the BERT model customized with a Siamese network for generating embeddings. And you need to check the page that tells you how you can use in semantic search, okay? And you have the background, you have the concept of vector similarity and blah, 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 blah. But you need to consider symmetric versus asymmetric semantic search, because this is important. So the first thing you need to check, and this is obvious, is if the embedding generator supports your language. If it's English, there's no problem. But if you live in Italy like me and want to generate embedding for Italian text, you need to take a model that is trained on multiple language, or maybe train it especially on Italian language. Now, let's keep in English, and let's say we are interested in English model, so we have no problem. And we need to understand the concept of symmetric versus asymmetric search. And first of all, we need to understand what is bi-encoding. That is a technique used by KernelMemory, by many RAG software solutions to use vector search to retrieve memory. The bi-encoding technique is designed to be super fast, because the concept, if I have all my segment of memory, so this is the fact I want to check, okay? So for each segment, I call my embedding function and generate a vector, and then I store this vector inside a vector database independently from the user question. So you need to calculate only first time and then index in the database. And then you can use the vector store capability for retrieving the piece of the piece of memory that are most similar to the question, and it's computationally faster, because actually you have segment of text containing information is the left column. You use a model to calculate embedding and you store inside the vector store. Then at question time, you take the query of the user, the question of the user, you generate the embedding of the question of the user, and then you go to the vector store and tells, hey, vector store, give me the 5, 10, 12 fact where the cosine similarity with the vector of the question is the most similar. So it is based on the fact that the embedding generator captured the concept of the phrase. So you hope that the context of the question, it will be the fact that are more likely to answer to the user of question of the user. They are the piece of fact which embedding is more similar, is nearer the question. So you just take the question, create embedding, and take the end top nearest vector for the vector store, and then take the fact associated with that vector. This is how bi-encoder work, but there's something to consider in this approach. If you use model from OpenAI or other publisher, probably those models are really complex, really good, and so you don't need to worry a lot about symmetric versus asymmetric search. But if you use BERT, and it's SBERT is one of the most used local model to generate embedding, you need to understand this problem. So symmetric semantic search means that your query and the entry and the fact are about the same length. And it's used to say, oh, I have a piece of text almost of the same length of the length of the facts. Remember, in the RAG, during the index phase, you take all your text, all your data, and you separate and you divide in segment of a given length. So all the facts are almost the same length. If the question of the user is the same length, you talk about symmetric semantic search. And if you have symmetric semantic search, you can use some kind of model. But usually when you do RAG, quite often you are in an asymmetric semantic search because you usually have a short query, like the example before. Can you please explain black sheep technique? This is the query, very few token, very few number of token. And then you have all of your facts that are longer token, maybe 384 or 500 token. And for this kind of scenario, probably you need an SBERT model that is trained on this kind of scenario. So the documentation tells you suitable model for symmetric semantic search, and you can check. And as I show you in the previous example, I've used the all MPNet based V2, and probably it's not the right choice because, as you know, in RAG, often I have short query versus longer piece of text. So you have all the documentation here, but well, probably this is not the model that is perfect for this scenario. So you can simply choose the suitable model for asymmetric semantic search, and they are model trained on MS Marco. MS Marco is a very large data set made by Microsoft that was created on real user query on Bing Engine. So it's a really widely adopted data set for training models on question and answer. So it's this scenario, short question and longer answer. And the usage is the same as before. So you use a sentence transformer. So there's nothing different from the point of view of Python code on how you use the model. And these are the performance, and you can say maybe the highest performance with various tests is the MS Marco Distilbert-based VU4. And so if you are in this situation, probably this is the model you need to use. And thanks to our structure, as you can see, you can simply change the DTO path to the SBERT PI Fast API server, just changing the model you want to use. So basically what you need to do is simply change the DTO you pass to your server. And in this situation, I choose the MS Marco Distilbert-based V4, and it will answer me. And as you can see, the number of dimension, the dimension is always 7C8. It is because BERT is as this dimension internally. But as you can see, this model has a longer sequence length, allowing us to create a segment of longer length. So this is simply. And how does it work? So why this works in Python so simply? I didn't change anything in the running SBERT example. As you can see, if you specify a different model name, the same code of the previous example, the sbert.py, simply load the new PyTorch model. So this solution is really, really easy to use because it is a shell, and then you can choose the model you want to use from external code. And the SBERT PI simply load the new model for you. And so it's really, really, really flexible. All the API I call accept the model name parameter, so I can send process sentences. I change the model name. As you can see, I have different vector. If you want to check, you can remove the model name and use the old model name. As you can see, you got different vector because you're using different models. So it's really simple. Thanks to the Fast API Python code, I can simply change the DTO to use a different model, so I don't need to change anything in production or in Python code. Another thing you need to take into consideration when you choose the model, it's not only the score because, oh my God, this is score 70, so it's probably be the best. And that's the worst way to choose a model. And as an example, you have model divided by how you can check similarity. So if your vector database is using cosine similarity, this model are tuned to be used in cosine similarity. And other models are tuned for dot product, okay? And that's the difference, and I need to give you some math to understand why. Since a vector is basically a point in an nth dimensional space, if I want to check what is distance between two vectors, because I want to take the nearest vector, I want to give the vector database one vector and answer and get as answer a certain number of vectors that are close, the closest vector. So if you have point in space, the easiest way to compute distance is the Euclidean distance. And that's the formula. It's not complex, but it has a problem. It has the square root, and square root is not so fast to calculate on a CPU or a GPU, so it is not probably the best choice. And you usually have another formula that is the cosine distance that does not take into account the real distance between the 2 points, but takes in consideration the direction. So it measures the cosine of the two of the angle formed by the two vector. And so, as you know, if they point in the same directory, the angle is 0 and the cosine is 1. And if they are opposite, the cosine is -1. And if you expand the formula, it's that one, and it still has square root. So it's not so good, but you have one caveat. So if you look at the at the first formula, it is the dot product divided by the product of the length of the vector. And so if the length of the vector is 1, you can say, okay, the denominator goes away, so you can really use a dot product for calculating the distance, and the dot product is more convenient in a computational way. So you can use normalized vector. So if your model is generating vector that has length 1, so it's all the points are positioned on a nth dimensional sphere of radius 1. You can compute the distance only with addition and subtraction and multiplication. So you can use CUDA or AWX or everything. But remember, you can use dot product only if the model generate vector that have module 1. So that's also another thing you need to take into consideration when you choose an embedding model. So if your vector store actually can use dot product, you could use the MS Marco Distilbert-based task B that has high score and is tuned for dot product. But usually you can use standard models tuned for cosine similarity, because all of the vector store, modern vector store, use efficient algorithm to calculate the distance even with not brute force. So they don't need to calculate the cosine similarity of every vector, but they use a much more smarter algorithm like HNSV, hierarchical navigable small word. So this is a consideration you can usually avoid. But if you know that your vector database perform really better using dot product, you can choose a model tuned for dot product. So always check thoroughly the characteristic of your model before using it, because you can simply choose a model that is not suitable or you are using in a wrong way, and so the result will be really, really bad. But thanks to our structure that I explained in the previous video, as you can see, to use another model, I can simply change the external embedding generator config, and I can specify the model name. So I'm using MS Marco Distilbert-based v4 because usually I use Elasticsearch or MongoDB Atlas as vector storage, and they perform well with cosine similarity, so there's no problem. And this is a very good model. I can simply change this configuration, and then the rest of the code does not change, because as you see before, the Python server accept the model name as parameter, so you can have another, you can simply change the model name. So you can rerun the example, and just changing the model name, you will have a different model. And this is super easy because you can simply I have the previous server running, so I need to close. As you can see, you can simply put this, this is in a configuration. So I use the BERT. I don't want to use a local model. I just care about the embedding in this example. As you can see, the result is almost the same. I'm indexing everything with the new embedding, and I've just changed the name of the model, and I'm using a different model. So I can post the same question. Can you please explain black sheep concept? And it is using another model, and it's going to perform, and the black sheep is a method within a class, blah, blah, blah. So it worked. And Actually, this example worked even in the previous video with the old MPNet model. But this is because I'm indexing only one document. So if you have only one document or a very small amount of memory, the difference between the various embedding model are not so great. But if you are indexing tons of document, you probably need to experiment with different embedding. And it's especially important that you prepare a set of question and the corresponding piece of text from your memory that you expect the vector database to give you, because you should create some sort of evaluation of your structure. So you can index your memory, you can ask to the vector store for all question which are the pieces of segment you got back, and you need to verify with a set of already checked vector, already checked piece of text, piece of memory, to verify that the embedding you are choosing it is correct for your situation. But as you can see, it's very easy to change between two different embedding model. So you just need to reindex everything for it to work. And if you know how kernel memory work, you can index maybe the very same memory inside your vector store in two different index using maybe two different embedding models. So you can pay more computational power during index phase and then have two index in your kernel memory that you can use for using two embedding. So you can pre-index with two embedding and then at query time choose which is the best. Okay, so you can experiment with this kind of situation. And the important thing is, thanks to the fast API server written with few lines of Python, you don't need to change anything in your C# code from kernel memory code, because you can simply change the name of the model you want to use, and you simply will use a different embedding, and the code in Python will take care of loading from Hugging Face the model from you and using that model. And this concludes this video. I hope you liked it. I'm waiting you for the next one.